Morning, everyone. This is the last day of our meeting, but maths never stop. So before Cinzia's last lecture, I'm happy to announce 2 meetings in algebraic geometry. This one will be in Bogota, Colombia, this 9 to 11 December. It's our 8th edition of our Bandoleros meeting on vector bundles and related topics. And next year, this is the web page for the CIMPA School next year, also here in Brazil, in Florianopolis. It will be in the first 2 weeks of August. Right, so I think this, and there will also be mini courses and about derived categories, Bridgeland stability, and various interesting topics. I don't know the deadline, but if you scroll up this page, I think in the bottom of the page, perhaps, that's it. Yeah, no, maybe in some other pages. So if you guys explore this site, you're gonna find the deadline. But the deadline is not very soon, so there is time. There is time. Also, there is the group picture today, right after Cinzia's talk. And I have a list here. And there's various schedule changes for today. And also, along the lines of the math never ends, the next ELGA meeting will be in 2027 in Medellin. Okay? Dates are yet to be defined. So there are various... Pedro not here yet. Yeah. So Pedro Rizzo will be one of the main organizers, the local organizer of this meeting. So there are various schedule changes that will update you throughout the meeting. I think the most important one is the dinner. Today we'll have different times. So the first batch is from 6 to 7 p.m. Second batch, 7 to 8 p.m. Okay? Because at 8 p.m. there will be a party for us downstairs at the pool. Everybody is entitled, birthright for 2 drinks at the party. But the vouchers for these drinks will be distributed later on, and further information about that later down the day. Okay? Yeah, so this announcement also for the transportation to Rio is very important. There will be 2 buses at 9 and 11. Please check the schedule on the meeting this meeting's website. Okay? But without without further ado, Cinzia, please start your last lecture. Thank you.
Thank you. Okay, so good morning, everybody. Today, as promised, we're going to focus on Fano fourfolds. Let me start with so I want to focus today more on the Picard number instead of the defect. So let me recall maybe that in any dimension we have finitely many families of Fano varieties. So here I'm considering only the smooth case. And also we notice that for Fano, the Picard number is just equal to the second Betti number, so it's a topological invariant, so it is constant in smooth families. And so it takes finitely many values in each dimension. And for the Pezzo surfaces, we know that there are 10 families. And the Picard number varies between 1 and 9. And 9 is achieved for the blow-up of P2 at 8 points. The defects are degree 1. And for Fano threefolds, we know that there are 105 families. And I want to recall a theorem by Mori and Mukai from 86. That if X, so let X be a Fano threefold, so if rho X is a 3, 6, then X is a product of a del pezzo surface with P1. Okay, so this is how, with this result, they ended the classification of Fano threefolds with Picard number bigger than 1, so that they should only work up to Picard number 5, actually. And so let me recall that the product of Fano varieties is again Fano. And conversely, we already mentioned that when X is a product, both factors are automatically Fano. So here, S is automatically a del pezzo surface. And also, so Fano varieties are simply connected. So if you think of the Kunet formula for the second Betti number, you see that the Picard number of the product is the sum of the Picard numbers. So here, the Picard number of S times P1 is just 1 plus the Picard number of S, so it is at most 10. So as a corollary of this theorem, we deduce that the maximal Picard number of Fano threefolds is 10. And between 6 and 10, we only have products of a surface with P1. Okay, so Mori and Mukai proved this result directly working on X, but I want to show that this follows easily from the result on the Lefschetz defect that we discussed in the last lectures. So if we have X a Fano threefold, then I left it as an exercise that the defect can be only rho minus 2 or rho minus 1. Okay? This is because you can take an elementary contraction on X. And then we know, we already mentioned that F cannot be small because we are in dimension 3. And so it will be either divisorial or of fiber type. And in both cases, if you think about it case by case, you can always find a prime divisor, so a surface that is sent either to a point or to a curve. so in the divisorial case, this will be the exceptional divisor, and in the fiber type case, it's even easier, okay? And then if you look at the push forward between the n1 of x to n1 of y, it's again easy to see that this implies that the dimension of n1 of dx is at most 2. So it will be 1 if D is contracted to a point, because all the curves in D will have class in the extreme array. So n1 of dx will be just the line spanned by the extreme array. And when D is contracted to a curve, then its image, the n1 of dx, will be sent in y to the line spanned by the class of the curve, and then the dimension will be 2. And so by this, we see that delta is at least rho minus 2. Okay, so this is the exercise. And then so we see that if the Picard number is at least 6, then delta is at least 4. And then we can deduce that X is a product. Okay, so this is just to recover Murray-Mukai's theorem. And also, I want to recall the number of families of Fano threefolds in different Picard numbers, just to have an idea. So here we have rho and the number of families. So in Picard number 1, we have 17. In Picard number 2, we have 36. In Picard number 3, we have 31. And then 13, 3. And between 6 and 10, we only have 1, the product. Okay? So we see that they are most of them are concentrated in low Picard numbers. Okay, so I want to present and discuss an analogous result on Fano fourfolds. So let's call it theorem A. That if we have a Fano fourfold, if the Picard number is at least 12, then again X is a product of the Pezzo surfaces. Okay? And so I prove this result for rho bigger than 12. And then in a joint work with Saverio Secchi that we just posted this week on the archive, we improved and also treated the case where rho is 12. Okay, and again, the Picard number of the product is the sum of the Picard numbers, so it's at most 9 plus 9. And again, we get as a corollary that the maximal Picard number of Fano fourfold is 18. And between 12 and 18, we only have products of surfaces. Okay? So the first question, I think, here is whether this condition is sharp. But we do not know because we have few examples. So let me note that all known Fano fourfolds, which are not products of surfaces, have rho at most 9. Okay? And so we do not know what happens in Picard numbers 10 and 11. So for rho equal 11, I also expect only products of surfaces. And for 10, I really don't know what to expect. So maybe there are examples and maybe not. Okay, more generally, I want to say that I would say that we have very few examples starting from Picard number 6. So what do I mean by few? So for rho equal 6, by this I mean not products, of course. So for rho equals 6, we have 12 known families. For Picard number 7, we have 3 known families, and these are new. 2 of these are new and are in this preprint. And in Picard numbers 8 and 9, we have 1 family in each row. Okay, so this should be compared with the fact that in low Picard numbers like 1, 2, 3, I think we have hundreds of examples. Okay, so there is really a big difference. So one of the reasons, I think, for which we have, maybe there are just very few Fano fourfolds in this range, but also one of the reasons for this lack of example is that, so I will describe these examples in Picard numbers 7 and 8 and 9, and you will see they are obtained via birational constructions, so that are not very easy neither to find nor to control. And so these are not fourfolds that you find embedded in some nice space like hypersurfaces and so on, and it's not so clear how to find them. Okay. So other questions so far? No? Yes? I cannot really hear.
If you have a family that gives product that represents products,
It stays, yes. So
are all the fourfolds in that family products?
yes, right. That's a good point. If you have a product of Fano fourfolds, the Fano deformations are still products of the same type. Okay. So in fact, we do not get non-products examples from them. Okay, other questions? So I will now describe this family with Picard number 9. It's actually the same construction gives a family of Fano fourfold in each Picard number up to 9. Yes?
So if I try to copy these results for like big Picard number, I have an estimate of what the maximum Picard rank is by taking products or surfaces.
Yes.
Is it known that for every dimension those are products, or it's not?
No, it's not. No.
Or that it's the maximum Picard rank, or no idea?
No. So we are far from being able to say something on like so strong on higher dimensional Fano varieties. So I think it would be a reasonable expectation to expect that also in higher dimensions with large Picard number they must be products. But I should say that I do not have so much. So already in dimension 5, I don't have so much experience on examples. Okay. But I think it still could be reasonable. The maximal Picard number is not known, but it is possible to give explicit bounds on B2 in terms of the dimension, but these are super large functions, because so the same proof that gives you boundedness, okay, also gives you explicit bounds on all the Betti numbers, because to prove boundedness, you basically you show that you can embed your Fano variety in a projective space with the degree bounded by a function only of the dimension. And then there are classical results based on Morse theory, and also there is a nice result by Fyodor Zak from, I think, more or less 10, maybe more years ago, that you can, when you have a smooth projective variety embedded, you can give explicit bounds on all the Betti numbers just in terms of the dimension and of the degree. So if you apply this to Fanos, but then this, I mean, are for sure very far from being sharp. So, yes. I remember I wrote the bound in dimension 4, and it was, okay. So other questions? Okay, yes. Yes, so the toric case, in the toric case, in fact, I proved the bound on the Picard number in arbitrary dimension a long time ago, I think right after my PhD. And so it is true in the toric case that the maximal Picard, so the maximal Picard number is twice the dimension. So if X is toric Fano, and equality holds only if n is even and X is a power of the del pezzo surface, the blow-up of P2 at 3 points. Okay, so this is the last del pezzo surface, which is toric. And then it is actually true what you expect in general. But the proof of this is completely combinatorial. So it does not give you an approach, at least it's not clear that it gives you an approach for general Fanos. And then there are some works, several works, I would say, to study when X is not a product, what boundary you can give on the Picard number. And this is an interesting problem. Yes? Yes, so it does not, so we say that Fano trifolds starting from Picard number 6, they are a product of P1 with a del pezzo surface. So if you again take a product with P1, it's still a product of del pezzo surfaces. So this is different only in low Picard numbers. For instance, here in Picard number 6, so in Picard number 5, there are 2 Fano trifolds that are not products, and they give you 2 examples with Picard number 6 that are products, but not products of surfaces. So I have not included them in this 12. But this makes a difference only in low Picard numbers. And I would say no, I don't have a specific method to detect them. Okay. All right. Other questions? So now I would like to, as I said, to explain this family. It's a very nice construction. So you start from P4, and you take are general points where R is at most 8, and you blow them up. That we call this X hat. Okay, so it's easy to see that starting from 2 points, this is not Fano, because if you take the transform of a line that contains 2 of the blown up points, that will not have, that will have intersection 1 with the canonical class. But still, so X hat, let me say, contains some bad curves. The transforms of the lines, the transforms L of the lines to true points, and they have the property that, so they have intersection 1 with the canonical class. They are isomorphic to P1, and the normal bundle is the sum of 3 copies of O minus 1. And also for 7 and 8 points, you also have the rational normal quartics. So remember that in P4, a rational normal quartic is determined by 7 points. So here you consider the transforms of the rational normal quartics containing 7 points. Okay, and they have the same property here. Okay, and these bad curves are pairwise disjoint, these curves, because they intersect in P4, but then after the blow-ups, they are disjoint. And then you can flip them and get X, which is smooth and Fano. And the flip is very simple. You just blow up these L's, and the exceptional divisor is a P1 cross P2, and you contract onto a surface here, which is isomorphic to P2. And this is exactly the same as the example that we saw yesterday. It's just the other way around. Yesterday, we started from the surface, and we flipped, and we got a curve, which was exactly with that properties. Okay, so I will call this X the Fano model of the blow-up of P4 in our points. And so the Picard number of X then is the same as the Picard number of X hat. So it goes from 2 to 9. Okay, and so X hat is not Fano, but it is log Fano. Because it's related to a Fano fourfold by flips. And in fact, Carolina has a nice paper with Alex Massarenti, 2016, I think, where they give explicitly a boundary delta on x hat that realizes the log Fano structure. Explicit boundary in x hat. Okay, and then we know that if we blow up more points, x hat is not log Fano. In fact, it is not a Mauridin space. Okay, and this was shown by Mukai. And also Anna Maria and Genia have a nice paper related to this. And so this tells us that we cannot do the same for more points, okay? Because it is a necessary condition to be related, in order to be related by flips to a smooth Fano, you have to be log Fano. So 9 is the maximal Picard number that we can obtain. Okay, and then later I will say more about the geometry of this X. And now I would like to describe these two new families with Picard number 7. So this fourfold is the only Fano fourfold that we know except products in Picard numbers 8 and 9. In Picard number 7, this is one of the families. And let me describe these other two families. So they are blow-ups of X6, which will be this X, so the Fano model of the blow-up of P4 at 5 points. So 6 is the Picard number. At the surface, at a smooth, irreducible surface, S. And I will describe what is the surface. So we describe the surface as a transform of a surface in P4. The transform of a surface A in P4. So I have to give you the two cases. And A So in one case, it is a general cubic rational scroll containing the points that we blow up, that are 5. Okay? And in the other case, it is a general singular K3 surface, sextic K3 surface. So this will be the complete intersection of a quadric and a cubic, and which is singular exactly at the 5 points. and has A1 singularities at the points. Okay, so these are, and I want to make some advertisement because, in this case of the K3 surface, we show that in fact you cannot do this construction with more points. So if you do the same like with 6 points, the fourfold that you get will not be Fano. Okay, so in this case, rho equals 7 is maxima. We show it. But in this case, we don't know, so we leave it as an open question. Does the same construction for 6 and 7 points give a Fano fourfold. Okay, so this would give examples with Picard numbers 8 and 9. Okay. Instead, we know that for 8 points, it cannot work. Okay, so this is, if you like this kind of questions, have a look at this fourfold. And in the preprint, we also have 2 other candidates. So explicit fourfolds that we leave as an open question whether they are Fano or not. So for some reason, we find them in some result, and for one of the other 2, we checked in low Picard number, it's actually Fano, but we did not get up to 9 because it gets more complicated. And there is a 4th one that we did not study at all, which is again a blow up along a surface of this Fano model, but it's more complicated because the surface is singular. But the fourfold you get is smooth. So we leave some possible examples as open questions. Yes? We don't know. We don't know what happens. Because we already need the Fano model to be Fano. And I think we need the generality in many cases. But we don't look at that. Yeah, in fact, I don't know. It's probably hard to see, even to give, because, I mean, for instance, for the scroll, you need generality also for the position of the points on the scroll, for the blow up to be Fano. And then, so it's probably even harder to write explicitly all the conditions that you need explicitly. Yeah. Yes.
Do you have a model-like description of those?
No.
Do you expect something?
I did not think about it. So Carolina is saying, let me repeat the question. So for these Fano models of the blow-ups of P4 in points, for each of them, maybe in large Picard number, there is a modular interpretation. This is due to Mukai. And this is also what we use to study them. For instance, the one with Picard number 9, it's a very clever idea of Mukai to interpret it as a moduli space of vector bundles on a del pezzo of degree 1. And then you can use the variation of the stability condition, the classical one, Gieseker stability, to control the birational geometry. So we know a lot about this example, the Neff cone, the moving cone, and so on. And So the question is, can you give also a modular interpretation of these blow-ups? But I really don't know. So what we found these surfaces by an explicit, so we have a classification result, which is like if you have a Fano fourfold with this and this and this property that I will not now explain, then we find three families, three possible families. And so these were two of these families. And the third one was this one with a singular surface. And I think this is the deepest result in the paper. It's a lot of work to find these three families. And then so we checked whether these families would be Fano or not. So, but we just find them by explicit study. So we don't know. Yeah. Okay, other questions? Okay, now we discussed examples. Let me say something on the proof of theorem A, at least strategy. It's an idea of the strategy. That if, so if rho is at least 12, then X is a product of surfaces. So first of all, we know that Fano fourfolds with defect at least 3 are classified. And they are either products of surfaces or have rho 5 or 6. Okay, so we can just forget about this case and just reduce to the case where delta is at most 2. So theorem A follows from this, and let's say theorem B, that if we have a Fano fourfold with the defect at most 2, then the Picard number is at most 11. Okay? So today, in the rest of the lecture, I want to discuss a little bit this. So you see that here there is a different point of view. So we do not actually want to prove that X is a surface, because that part is taken care of in this part using delta. We want to bound the Picard number of a Fano fourfold with suitable assumptions. And also, if we improve this 11 here to 10 or 9, less than 9, it's impossible because we have our example. Then we improve also the main theorem, the bound in the main theorem. So it's really here where you have hard work. And yes, so the proof of this theorem has taken many years, many works, a lot of work. So of course, I will not explain the whole proof. I will just give an idea of the beginning. Instead of focusing on the last part, I will focus on the first part. And so the strategy is again using birational geometry in the sense of MMP, and do a case-by-case analysis, okay? And this assumption is crucial in many ways, and in particular, it allows to reduce a lot the number of cases that you have to look at. So otherwise, it would be impossible to do the same without this, okay? So let's just start and see what we can what is easy to say? If we have X a Fano with delta at most 2, and I will, we can start just by looking at the elementary contractions of X and see what we can say depending on the type of contraction. So the first remark is that, so suppose that X has an elementary divisorial contraction that sends the exceptional divisor to a point or to a curve. So if you have E, the exceptional divisor, so the dimension of f of E is at most 1. Then exactly with the same argument that I explained before for threefolds, then we have that the dimension of N1 of the exceptional divisor is at most 2, but delta is at most 2, and so the Picard number is at most 4, very low. Okay, so this case is easy. And what about contractions of fiber type? So again, suppose that X has an elementary contraction of fiber type. So if the dimension of Y is at most 2, then you can, it's easy to have the same argument. If the dimension of Y is at most 2, you can easily find a prime divisor that is sent to a point or to a curve. And then, exactly like in the other case, we get rho x at most 4. And if Y is a threefold, then with some more work, but it's not actually difficult, one can show that there exists a prime divisor in X such that the dimension of N1 of the X is at most 3. Okay? And so with the same type of arguments, slightly longer. And then again, delta is at most 2, so rho x is at most 5. Okay? And so we see that with these two remarks, we see that if rho is at least 6, X can have only 2 types of elementary contractions. Because what is left outside the two remarks is the small case and the divisorial case when the exceptional divisor is sent to a surface. Okay? And this is what I call the type 3-2. This is a terminology which is often used for elementary contractions. So 3 is the dimension of the exceptional locus, and 2 is the dimension of its image. So this means divisorial, and f of E is surface. Okay? So in many, this bound rho at least 6 appears many times precisely for this reason. So in lower Picard numbers, you have many more phenomena, many types of possible elementary contractions that disappear starting from Picard number 6. Okay? And then now what can we do? Because in this case, we have no special prime divisor. In this case, we cannot control the Picard number of the exceptional divisor because we don't know what is the surface. Okay, and then we need to consider not only x, but the fourfolds that we obtain from x after flips. Okay, so it's necessary to work also with these fourfolds. And now I will make some examples from using this Fano model of the blow-up of P4 in points to show what can happen. So we consider x. The are points. And yes, maybe let me say that what is the Lefschetz defect of this delta? So up to 5 points, this x is toric, because when you blow up P4 in 5 points, you get a toric variety, and then the flips preserve. Okay, so in this case, it's easier to compute, and we know that delta is 1 for rho at most 6, which is the case where x is toric. And then for the other cases, 7, 8, and 9, delta, I don't know, must be 0 or 1. Because as I said yesterday, it's not so easy to distinguish between these two cases because delta equal 1 gives very weak conditions. And they are satisfied by x. So, okay. And also, I want to say that starting from Picard number 4, this x has only small elementary contractions. Okay, so there is really no special divisor to look at, no divisorial contraction. Okay, but remember that x is related by a sequence of flips, just by construction, to the blow-up of P4 in R points, which was x hat. So this contains, for instance, the exceptional divisor over P1, which is a P3. Okay? So what I want to stress is that the bound on the Lefschetz defect tells us properties of Picard number of divisors in X, but it does not hold anymore when we do flips. You see here we have a divisor with Picard number 1 that could not exist in X, and by the same principle, so this some of these elementary contractions that we excluded in X, we can find them after flips. For instance, the blow-up of a smooth point, okay? Because what is the geometrical picture? Here we have this P3 and this E1. So it will intersect many of these bed curves. All the transforms of the lines that were through P1, and then when we flip, we blow up the curves, and then the divisor is blown up at these points. And then in X, its transform, it contains these surfaces isomorphic to P2. So this will be the blow up of P3 at some points. Okay? And then the Picard number increases in X. So this is what happens geometrically. And just as a terminology, I will call such a map a sequence of flips, a small q-factorial modification. Small. And this can refer to the map or also to X hat. So it's just to avoid to repeat each time a sequence of flips. Okay. And I want to make another example, still with this X. So in this sequence of flips, you can find an intermediate model. Okay, such that this X tilde has a P1 bundle structure. Onto the base, which is the blow up of P3 at r-1 points. So let me explain geometrically why is this. But I need a big blackboard, so I'll go here. So if you start from P4 and you blow up only the first point, okay, and then we know that this is a P1 bundle over P3. Because we are resolving the projection from P1. Okay, and then when we blow up the remaining points, okay, we can flip not all the bad curves, but only the transforms of the lines P1 through P1 and one of the remaining points. Transforms of P1, Pi. Okay, and you get this X tilde. And here in P3, you can consider the images of the remaining points, P2 to PR, say Q2, the images under the projection. Okay, and you blow them up, and this is Y. QR. And then this map, this P1 bundle here extends to a P1 bundle here. Okay, let me also make another drawing. Because this is very explicit. If you consider, for instance, the point Q2 in P3, its fiber here is the transform of the line P1, P2. So this is in the blow up of P4 at P1. Okay. This is a transform, which is a fiber, and here you still have P2, okay? And when you blow up P2, you get a P3, E2, with this transform, which has become one of our bad curves, okay? And when you flip it, this P3, as I said before, is blown up in this point. And here you get the blow up of P3 at one point, which is a P1 bundle over P2. So this extends over a P2, which is in Y, which is the exceptional divisor over Q2. Okay? So this is a nice explicit projective geometry. And why am I saying this? Because this is another example where we have our Fano fourfold, and recall that all elementary contractions of X are small, but after flips, we can get a very nice elementary contraction of fiber type. Okay, so a priori we don't know what we will get after flips, so we can get a lot of nice geometry. Other questions? Okay, so let's go back to our general case where X is a Fano fourfold with defect at most 2 and Picard number at least 6. And so there is a fact that I will not prove, that even if it may happen, like in the example, that X has only small elementary contractions, but you can always find, after flips, an elementary contraction which is not small. There exists always some small q factorial modification such that X tilde has a non-small elementary contraction. Okay, this is easy if you know Mori ring spaces and the chamber recomposition, because you only have to take a model that goes to the boundary of the movable cone. And so now we can see what we can say about elementary contractions of X tilde. So we take this F elementary contraction. So it can be divisorial or of fiber type. And let us first see the divisorial case. Okay, so let me call E the exceptional divisor and phi the composition of flips. Okay, let me recall that I say that we know how this modification is achieved by a sequence of flips all of the same type. So we know that if I call A the loci, the closed subset where the inverse of the map is not defined, is not, so A will be X tilde minus the domain, it's like yesterday. We know that this is a connected union, a union of connected components where these curves have intersection 1 with the canonical class, and the Li are pairwise disjoint. Okay. And now, if I have a curve in X tilde which is not one of these curves, then I can consider its transform in X. Let's call Cx the transform of C. And again, I can compare the anticanonical degrees. And I have a fact which is in fact the same that we used yesterday in the study of the MMP, that the anticanonical degree in X is smaller or equal than the anticanonical degree after the flips, and strict inequality holds if the curve intersects one of these S. Okay, so you see that these fourfolds that we obtain from a Fano fourfold after flips are not Fano, but are really very special because they have these finitely many curves which have intersection 1 with the canonical class, but on the other hand, all the other curves have positive intersection with the canonical class. And also, if so in particular, this says that this intersection is positive and it is at least 2. And this gives a lot of conditions on the geometry of X tilde. Okay, so this is what I'm going to use to study what F can be. Other questions? So in particular, we see from this property that F is always K negative. Because the curves contracted by F will cover a divisor, so they cannot be, they cannot contain any of these curves, so they will be, they will have a positive intersection with minus K. Okay, and so here we have the exceptional divisor, and here we have its transform, okay? And then we compare the Picard number of EX and of E. Okay, sorry, I will start from the case, suppose that the exceptional divisor is sent to a point or to a curve. So I want to study first this case because this is a case that we cannot have in X. And so we know that the dimension of N1 of EX tilde is at most 2 because of this property. And here in X, we have the dimension of N1 of EX X is at least rho X minus 2 by our assumption on delta. Okay, so rho is at least 6, so this is at least 4. Okay, and so this means if you do the same analysis basically that we did yesterday using these flips, this means that there exists at least yes, rho minus 4, which is at least 2 Li's intersecting E and not contained in E. It's like the picture that I made before for the P3. So it will be like this. Okay, because this is what makes this dimension increase after the flips, because then here E has positive intersection with these curves, and they are outside, the classes of these curves are outside of this space. After the flip, E will have negative intersection with the small extreme array, and we contain these surfaces, and this is what makes this increase, okay? And so you see that E is our exceptional divisor. So for instance, if I consider this point, there will be a fiber. I mean, for instance, in the case where the image is a curve, there will be a two-dimensional fiber. And I have conditions on the anti-canonical degrees of the curves that touch this point because of that. In particular, it cannot be 1, because if the curve intersects L1, it cannot have anti-canonical degree, 1. And so this can be used to reduce a lot the possibilities for F. So let me write something. If C contained in E is contracted, and intersects some Li, we have at least 2. And these restrictions can be used to classify F. So I will just do one example. If, for example, suppose that E is P3, okay, and we have an elementary divisorial contraction that contrasts the P3 to a point, okay? Then, if you write the normal bundle, this will be negative. Yes. But since the contraction must be K negative, you don't have many possibilities. You know that A must be 1, 2, or 3. This depends on the fact that F is K negative. Okay. But now, if A is 3, it's easy to, if you do a little bit of computation, it's an exercise. A line in this P3 will have anti-canonical degree 1 in X tilde. But this cannot be, because I can always find a line intersecting one of these L's. Instead, if A is 2, then you can do the same. The anti-canonical degree, now it will be 2. In X tilde, okay? But again, you can exclude this because you know that you have at least 2 of these exceptional curves intersecting E. So you can take the line through 2 of these points in E, okay? And because it intersects two of these curves, the anticanonical degree going to x must degree at least by 2. Decrease at least by 2. And so again, it's impossible. And so we must have A equal 1, and F is just the blow up of a smooth point. Okay, so this was an example of how these conditions on the intersection with these special curves, which in turn comes from our bound on the delta, on the defect, gives you a lot of conditions of anticanonical degree of contracted curves, and in turn, it can be used to classify F. And now I will just state what you get in the end. In the end, we get for this divisorial case where the image of the exceptional divisor cannot be a surface. So if there are only 3 possibilities, so the first is that just the one that we saw, so Y is smooth, F is a blow up of a smooth point. And the second, that again Y is smooth, and F is a blow up of a curve, of a smooth curve. Irreducible. And then the last case, Y has an isolated singular point. Locally factorial, terminal singularity, and E is isomorphic to a quadric, to an irreducible quadric, and the normal bundle is OQ of -1. So these are very special among all possible K-negative divisorial contractions in dimension 4. So it's really very restrictive. And let me also say what happens if the dimension of E is a surface, if the image of E is a surface. Then in this case, on an open subset, the map is just a blow up of a surface, okay? So the general non-trivial fiber will be a curve, a rational curve, which has anticanonical degree 1, okay? And so in fact, E is covered by curves of anticanonical degree 1. So it must be disjoint from these bad curves. And in fact, one can see that this divisorial contraction you already have in X. So there exists Yx. So this is a small q factorial modification, and also here. And these flips are disjoint from the exceptional locus of the map. And this fx is an elementary divisorial contraction of type 3-2. Okay? So in this case, we cannot classify the map, but at least we say we already had it in X. And so you see that altogether we have 4 types of possible elementary divisorial contractions in X tilde and in X. And so the transforms of these exceptional divisors will be fixed divisors in X. Okay? And so if we change a little bit the point of view, this gives a classification of the possible fixed prime divisors in X. Because when you have a Fano fourfold and you have a fixed prime divisor, you can always do a sequence of flips and it will become the exceptional divisor of an elementary divisorial contraction. Okay? And in fact, one can see that these 4 possibilities are unique. So if you have in X a fixed prime divisor, it's precisely one of these 4 types. Okay? So either it's already in X the exceptional divisor of an elementary divisorial contraction onto a surface, or after flips, it becomes the exceptional divisor for exactly one of these 3 types. Okay? And in fact, this classification in 4 types is crucial for the rest of the analysis. Okay? And I use it again and again because it gives a very explicit description of the divisor. Okay? And so in many times, and then of course, to bound the Picard number in general, there is still some work. But I wanted to explain this because it's really a key result in the sequel of the proof. And so I will maybe not explain the case where F is of fiber type. Instead, I will just give an idea of how one proceeds. So once you have this classification for these fixed prime divisors, your goal to bound rho x is to construct some fiber type contraction on some after flips, so on some X tilde. And in general, this fiber type contraction will not be elementary because the elementary case is too special. But it's easier to construct a fiber type contraction which will not be elementary. And then there are, so maybe let me just. So this is just a general strategy that I use in many cases. If you manage to construct a fiber type contraction, you can always assume that F is K negative. This is not a problem. And then X tilde is smooth, F is K negative, so the general fiber F will be smooth and Fano. So you know the general fiber, okay? But in general, it's not so easy to relate the Picard number of F to the Picard number of X and that of Y. Because think that you have like a P1 bundle and then you blow up points and then the general fiber do not see what happens outside the general fiber. So there are some techniques that one can use to handle this. So in many cases, you can actually manage to bound the Picard number if you have some knowledge of F and you study the geometry of Y, and F you know. Okay, so this is a strategy that I use a lot. And this classification that I explained for fixed prime divisors is very useful to study Y also. Because you can play a lot of two-ray games, say. So if you study the contractions of y, you can try to lift and see what happens. And the possibility to control these divisorial contractions above is very useful. So this was just to give an idea. And maybe this is what I wanted to say on the proof of the bound on the Picard number. And maybe let me also say something on the research directions in dimension 4. So, first of all, I think we have to understand what happens in Picard numbers 10 and 11. I think this is possible. It's just a question of work. And then it's an interesting problem to construct new examples, new families, in the range, say, in large Picard number. And then maybe it's possible also to have a classification in this range. For instance, for Picard number at least 7 or for Picard number at least 6. If there are not so many families using these techniques, it's maybe possible to have a classification, but this I see as a maybe harder goal. Okay, so this is what I wanted to tell you.